went and downloaded Ricardo's notes on regularized Stokes slits and did your homework and computed what I wrote on the board. But let me just recap and say again, now you're all experts in the steady Stokes equations, and we're thinking about having a right-hand side, we're thinking about having a collection of localized delta function-like forces. And what we did was we recast this, and instead of looking at a force centered only at x0, only being applied at xk, at a point xk, we're going to mollify that or regularize it and imagine that we're going to have a force spread over, say, a ball of radius epsilon. Now, we could use functions that are compactly supported. So when I say a ball of radius epsilon, even if we are using these regularized blob functions or shape functions that have infinite support, most of the area under the curve, or most of the mass will be centered around some ball. Okay, so this is what I went over or wrote down really quickly for you, that we look at a force applied over this region, this radius epsilon, for some shape function or blob function or whatever name you want to use, whereas it's like a delta function. So here, for this choice that I wrote on the board yesterday, you can do the formal calculations like I did for the case of the delta function and come up with an analytic solution to the Stokes equations in terms of this parameter epsilon. And the important features that we have, and I'll say this again, is that this is an exact solution to the Stokes equation, and it is everywhere incompressible, and it is defined everywhere, even at x equals 0. So R is just, in this case, R is the norm of x. Okay? So here, even when you are applying a force at the origin, the velocity field is finite at the origin. And this formulation is very appealing because we didn't just go into the classical Stokes slit and regularize it. We have an interpretation that this is a solution to the Stokes equation with that particular forcing. And these properties, the fact that this formula is actually incompressible and so on, leads to nice features in the numerical method. So because the Stokes equations are linear, and if you have a collection or a sum of forces along the curve or along the surface, then your solution is just the sum of the Stokes slits with different strengths. Okay, so now what I've done here is a little bit nasty again. I changed my forces from F's to G's. And what we have then is we can compute the velocity at any point J. I'm sorry, we can compute this, sorry. I could compute the J component of velocity at x naught anywhere, even at the points where we're imposing force by this linear relationship with the forces. So what we have is this. So if now I take U to be the vector of velocity vectors at all of the endpoints where I'm applying force, this is related by this matrix equation to the velocity, to the force vectors G. So this U and G are very long vectors that have 3 times m components, where m is the number of points. Yeah.
So I don't understand what's the problem if you even have delta functions. So even if you have delta functions, your problem will be singular in a set of measures 0. So you can still integrate it, you can still do everything. Right?
That's right. That's right, but you have problems near this form. You have problems evaluating exactly the velocity at the point where you're exerting force with the Stokes slits. This is the basis of boundary element methods where they deal with these singularities. I'm giving an alternate formulation where now we don't have to we don't have to much worry about these singular integrals. From the outset, the way we're formulating the problem, there's no singularity. So this linear relationship between velocities and forces does not just come out of the regularization. This is true in even if you have delta function forces. But a couple of comments here. Unlike the Navier-Stokes equations, well, here we have a linear relationship, but what's also very appealing is that we can specify forces like we were doing in the inverse boundary calculations with Navier-Stokes equations and then come up with the velocities everywhere. In the Navier-Stokes inverse boundary method, we didn't have a linear, just a matrix equation. We had to solve the full time-dependent Navier-Stokes equation. But here, by taking this relationship and inverting it, we can also specify the exact kinematics. We can specify velocities at points and figure out what forces need to be exerted at those points in order to achieve the specified velocity and kinematics. So for zero Reynolds number flow, we could ask the question in the opposite direction. If we have a body and we want to specify velocities everywhere, what forces need to be exerted at those points in order to get that velocity, and then using this type of relationship, we could get the velocity of the fluid everywhere. So I'm going to show you some simulations there. Okay, so do you all know what this is? This is a microorganism. It is about 12 centimeters, and this is
12 centimeters? 12 centimeters?
Sorry. Centimeters. What are units between friends, right? Sorry. This is a spirochete. So spirochetes are bacteria. They're very nasty. They're the causative agents of Lyme disease, syphilis, and if you scratch the front of your teeth right now and put it on a microscope, you find some of these spirochetes. They're not all bad.
Kill it.
Kill it. But so this is a micrograph. We collaborated for some time with Stu Goldstein, who's a biologist at the University of Minnesota. And I'm not going to tell you too much about spirochetes, but I'll tell you a few things. They are bacteria. They swim by the action of flagella, just like flagella of E. coli, that are rigid and rotate. But one of the amazing things and what makes spirochetes so nasty is their ability to swim through mucosal surfaces, and they are very nasty and are resistant to lots of antibiotics, and I'll show you what I mean by this. So here's your usual bacterial cell, like the bacillus that we saw in the collective behavior, and E. coli and so on. And while E. coli have many of these bacterial flagella, they're attached by some rotary motor. They spin one way, the cell body spins the other way, and they swim. So in fact, what you're seeing here is something like this. Here, the cell body of the spirochete is itself helical. Okay? So that long thing that you're seeing is the cell body. And at each end of this particular species of spirochete, you have two rigid flagella. What I've drawn here now is not correct. So at each end, you do have these flagella, but rather than emanating outwards from the cell body, they wrap around the cell body, back on it, on either end, and then there's a plasma membrane surrounding the whole thing. So one reason these guys are such great troopers is that their flagella are internal. They're protected. And so what you see on each end here, you see this looks like some sort of spaghetti, curly spaghetti here, but at each end you see a hook type region here and a forward region where things are bent. That's the region where these two flagella are actually operating internally. And if you analyze the tip here, this front in the direction where it's actually swimming is actually a superhelix. So the cell body itself is helical with a given with a it's a right-handed helix. But then when the flagella on this side wraps around it, the anterior helix has a bigger radius, which is actually left-handed. So it would be great to understand the motility properties of the entire organism, and I don't have time to tell you about all of our analysis there. But what I'm getting at is there's just some interesting fluid dynamic questions that come out from just spending time looking at these creatures, looking at helices moving in a Stokes flow, looking at superhelices in a Stokes flow. So let's ask this particular question. So as mathematicians and theoreticians, we could just say, let's get rid of all of the complications and let's just look at the center helix. Straight helix, center line is a straight line. And we asked ourselves this particular question. If we take a 12 micron helix, center line 12 microns, and we look at, we fix the amplitude here, and we're basing this on this leptospira, and we ask the question, how many rotations? So let's imagine that the motion of this creature is a rigid rotation. We ask how many rotations are required for it to advance one body length. And then we asked for this geometry, but then we ask this question.
So helix radius means the pitch of the helix? Helix radius means the pitch of the helix?
Yeah, that's the...
Is this distance?
What I can't understand. So we have a particular helix, and we're going to fix its radius. And here in this picture, I'm just saying it also has a given. It's not a line. It's got a given thickness, so it's a tube, a helical tube. And just a question we're going to ask is this. Fixing the radius, I'm calling it the amplitude, fixing the radius of this helix, its actual thickness, and its actual finite length. My question is, if you put more and more turns on the helix, and you ask the question, for each of these geometries, how many turns does it require to move one body length? So before we go ahead and try to do calculations, let's think about this for a second. Because if you had 0 pitches, you would have a straight cylinder, right? So it doesn't matter how many times you turn it, the fluid's not getting pushed in one direction. It should go nowhere. Then you put more and more turns on this. As you put more and more turns, you can't put an infinite number of turns because this has a finite thickness. And I would make the analogy to telephone cords, but I realize that probably most of you don't even remember seeing them.
We have it there.
There's one there.
Yeah, look at that. Wow, that's retro. Okay. So the thing is, if you put more and more turns, again, and you turn this, you're going to present to the fluid something that looks like a solid cylinder but fatter. So you would expect that somewhere in the middle you'll have an optimal number of turns. this is, not a very complicated problem, but we sought to solve this by coupling this to Stokes equations. So we know with these regularized Stokeslets in our formulation, I'm not saying you couldn't do this problem in other ways, in boundary integral methods and so on. But let's think what we have. We have a mechanism for relating forces to velocity, based purely on the geometry by this regularized Stokelet matrix that depends only on the position of the points. For those of you who think about Stokes flow, we can say that we have this, we can write it as this, that if you look at the total force that's related to the actual, of an object, so this is the integral of the force here, that's related by these resistance matrices, or these matrices whose components depend only on the geometry. So the force is linear related to the velocity and the angular velocity of the object. Similarly, the total torque is related linearly to the velocity and the angular velocity, and you can convince yourself that these matrices are related like that. Okay? So what we can do here is the following. We can assemble these resistance matrices in a methodical way by taking our object, so whatever object this is, where we've discretized it and we've got a bunch of points on it, we could at each instant impose a velocity at every point of 1, 0, 0. We could then compute, what does that mean? Impose a velocity, take this thing and drag it instantaneously in the x direction 1, 0, 0 without imposing any angular velocity. So if we put in 1, 0, 0 to u, we could figure out what the first component of this resistance matrix is, because when we specify the velocities, we get back, using the Stokes formulation, we get back the forces at every point that gave rise to the 1, 0, 0. So we add them up and get force here, and then we figure out what T is. So these are very quick calculations in the sense that all we're doing is solving a linear system. And we could assemble these matrices related to that geometry. If we wanted to as well, we could figure out flow fields and so forth. But now then, we ask the question, once we have these coefficient matrices, we say, now, if we apply an external torque, because we have to do that here, we have a rigid cylinder and we want it to swim, so we're allowing ourselves to apply an external torque. What happens then if this was free swimming? So we go ahead, and once we have these matrices, in free swimming with an external torque applied, we could compute what the translational velocity is relative to the rotational velocity, meaning how many turns are required to swim one way. So I'm not showing you any of the numerical calculations here, but I hope that you can see that this is a doable problem. Given velocities, you could compute forces. Okay, and so here is the number of rotations required to go one body length. Here are the number of pitches per body length on this 12 micron given radius tube. And what you see is that you do get this shape that you expected, because here near 0 it wouldn't be optimal, and as you get more and more pitches it wouldn't be optimal. So we get kind of a flat bottom here, and the real spirochete actually sits over here. So that particular leptospira, the cell body isn't free to, the geometry of that cell body is not free. And so most of the time they have about 17 pitches per body length. And so that's where it sits, and if you look at the swimming velocities, how many times it rotates per body length, the experiments are about here. Now, of course, here in this model, we haven't taken into account the anterior helix and the hook and so forth. So this is just an interesting calculation. Okay, so now let's look at this question. Before putting the whole thing together, before putting the whole thing together, I told you at this anterior tip, I wish I had this magnified, we have a very pretty geometry. We have a left-handed helix, but then we take, instead of taking this axis here that's straight, we have a left-handed helix, but we take this axis and turn it into a larger radius right-handed helix. So this was on my mind a few years ago when I got blown into New York City because of some little storm that we had in New Orleans. And I talked to Mike about this problem. And here is a nice thought experiment, and I'll tell you about the experiments that were done in the AML lab at Quran with Sunny Young, who was at Quran at the time. So here's my question. Suppose you have, I wish I had a real helix, suppose you have a helix, say left-handed. If you turn it in one direction, it will swim in a particular direction. I'm not going to get it right, left or right, I always get confused. If you turn the handedness, as it spins, will tell you which way the water is being pushed back and which way it will go. So now you take that and you start gradually making the center line of it, you start wrapping it into a helix in the opposite, that has the opposite handedness. So if you do that mildly, if you take the center line and you turn it into a right-handed helix, when you rotate it, that right-handed helix would swim in the opposite direction. So the question is, if you take the innermost, the skeleton helix, and increase its radius, at which time will that override the direction of swimming and change it from going one way to the other? So you have two helices, so let me show you this. So here's the cell body, let's say, that has a particular handedness. Then we're going to take that, and instead of having a stick or a straight stick as its center line, we're going to look at an axial helix of a bigger radius. And we're going to wrap that around this axial helix and very carefully unravel it from here. And so this is what we're calling a superhelix. So this, what I'm showing you here is, obviously it's a thought experiment, but this is the actual way that this was manufactured in the lab. Okay? And so what we would like to do then is to drop this in a tank of very viscous fluid and see which way it rotates. Okay? What happened was that this tank of, Michael, what was your name?
Silicon oil.
Silicon oil. You couldn't easily drop this straight. So Sunny figured out, rather than dropping it, put it on a pulley on a very thin string and let it sink down to the bottom. So instead of dropping it where you have no control, pull it up and then look to see which way it rotated. And here are movies, and I will tell you, I look at these a lot, and there are weird effects that I can't see the direction of rotation, but maybe you can. So, well, now I stopped the movie, and I can show you all later if you want. So here's a case where the axial helix has a larger radius than this one, and in fact, this is rotating in counterclockwise when viewed from above versus this. So experimentally, we were able to get this transition of direction of rotation based upon the radius of the axial helix. I had fun watching Sunny do these experiments. So again, another good test problem. So I'm always preaching about having simple test problems, if you're trying to do the very complicated multi-physics, multi-scale biological models, it's really good to have very simple, clean fluid dynamic tests. And so we compared our results. Just look at this top graph here. So for different radii, so the bottom axis basically is a scaled radius of the axial helix. So 0 would mean that it was straight, the axial helix, and this is it getting bigger. And we look at the rotational velocity over the translational velocity. Okay, important. And here we expect that this will change sign for some threshold, for some critical value of the radius of the axial helix. And so just look over here. And what you see, here's 0, and here you see dots, triangles, and squares, okay, or circles, triangles, and squares. So there's a few lessons to be learned here. That let's look at the triangles first. The triangles are the experiments. Okay, so this was what was modeled in that tank with silicon oil. The circles are the Stokes-Slit calculations, so solving the full fluid dynamic equations. And we see that we've got pretty good, almost excellent agreement. What I want to show you here is these squares. These are the resistive force calculations that Dan was talking about yesterday, by taking your object and splitting it up into independent cylinders that move in different directions. And so there is a lesson to be learned here. For axial helices that are basically straight, so there's not much curvature in this superhelix, the resistive force theory, like the regularized Stokes-Slit, fits the experiments very well. But as the geometry of the object gets more curved, gets more complicated, the resistive force theory gives you the same trend, but it completely misses the transition of rotation directions. So while resistive force theory is easy back of the envelope, or maybe not back of the envelope, but a 5-line MATLAB code to do, and it gives you ideas, you have to use it carefully. You have to understand that this is an approximation. Yeah?
It's the empty, are those circles or empty squares or empty circles?
I don't know. These look like squares to me. So this is the resistive force theory calculations. Okay. So I thought that that you would like to see this. So again, it's always very appealing to do the quickest calculation first, and many times that will be enough. But again, another moral is that maybe until you've done the full calculation or the full experiment, you don't know whether it's enough or not. So do the quick calculation for sure, but always remember that that's not full physics. So now I promised last time that I was going to talk about dinoflagellates. Okay, I can leave spirochetes, and if anyone wants to hear any more about them, I'll tell you what else I know. But let's go on to dinoflagellates. So I talked a bit yesterday about the diatoms, those spaceship-looking things with spines and so forth, in terms of phytoplankton and nutrient uptake. But Lee and Pete, our oceanographer colleagues, are very, very interested in the flow fields around dinoflagellates, understanding how they uptake nutrients that are around them, how they behave within vortical flows and so forth. So here are some pictures of these very beautiful creatures. So these, to give you a scale, I believe these are about maybe 50 microns. They're kind of small. And these are eukaryotes, and they have this beautiful arrangement of flagella. They've got one around their waist, These are eukaryotic flagella with motor proteins all around them. And so this I'm going to call the transverse flagellum. And then they have another flagellum emanating out from the bottom of the cell body, which behaves more or less like a sperm flagellum. So they've got one helical flagellum around their waist, around their equator, and one coming out. So what is the function? If you look at these, how do they swim? And what is the function of each of these two flagella? So I thought that this had been well understood when Pete introduced these to me today. So I'm quoting now from Tom Fenschel's paper, How Dinoflagellates Swim. This is 2001. If you look at a single dinoflagellate, it swims in a helical path. Okay? And as it swims in this helical path, so it swims up, but it also rotates around its axis. Okay, so you have, think about having a sphere with this helical belt around it and another helix down there. So the question is, what is the function? What is each of the flagella doing? How is it contributing to this motion? So I'm quoting Fenschel. The transverse flagellum causes the cell to rotate around its length axis. So the transverse flagellum is there. The trailing flagellum is responsible for the translation of the cell as it moves up. Right? This makes sense because I'm thinking, okay, we've got this helical, if we have a helical straight flagellum and it rotates, it's going to go this way. So if you take that helical flagellum and you turn it into a circle, the wave's going to pass in this direction and it's going to turn in that direction. So this seemed completely plausible to me. But then I looked further, and in 2004 there was a group in Japan. The functional roles of the transverse and longitudinal flagella in the swimming motility of some sort of dinoflagellate. The transverse flagellum works as a propelling device that provides the main driving force or thrust to move the cell along its longitudinal axis. Longitudinal flagellum works as a rudder. So these are conflicting points of view. Right? One says that this helical flagellum around the equator is causing it to rotate. This one here says that's giving the main thrust to make it go forward. So my question is, which is it? So some of you have seen this before. Which is it? How many of you think it causes it to spin? How many think it causes it to go up? How many of you think that it does a little of both? Okay. So this is pretty interesting, right? These papers are from the 2000s, and I was sure that somebody in the UK, out of Cambridge or somewhere in JFM, if I look close enough, that someone has looked at this problem about waving cylindrical rings in the Stokes fluid. And in fact, they haven't. So the beauty of theoretical physics and math is we could just get rid of all of the distractions. So we're just going to look at a ring. I will tell you that Pete Umars at Maine was not at all interested. When he saw us getting rid of the cell body, he was not happy. But we still wanted to solve this problem. So now what we wanted to do is to take a flagellum like this, turn it around on itself, put it in a Stokes fluid, passing a wave around it, not a rigid rotational wave, but like a waving sine wave with an out-of-the-plane component, so this helical component. And what we wanted to do was to actually specify the kinematics here. We don't want fluid structure interaction. We want to specify the dynamics of material points on this ring and compute the overall fluid velocity.
Right, but it's a material deformation. Right?
It
You're
is a
deforming the material.
We are deforming the material in a specified way. It is not rigid. Okay? So we built this, discretized this wing. Let's see. Okay, this is to remind you, if you haven't, for people who haven't been listening to me for days, that the wave goes this way and it goes in this direction. Okay? So here's the geometry. This green band is just a way to show you the radius of this helix is. So we can write down for the center line of this cylindrical ring, we could write down it's just a formula as a function of time. And we're passing a wave in a certain direction, and there you have it. Specified kinematics of the center line. We are actually going to put we're going to put rings around the center line so that this tube has thickness. So then we could compute, given the kinematics, we could compute the velocity, the tangent vectors, or the velocity everywhere on here, and in fact on the rings that make up the center line. But that's not so that's not enough, because we want to understand how this thing swims freely. So we're going to have a linear relationship between the velocities at each of these points and the forces exerted at those points, which we're going to solve for. Then we have other constraints. We want the sum of the forces to be 0, and we want the sum of the torques to be 0. Those are 6 constraints, 6 scalar constraints. But from that, in order to satisfy that, this ring translates and rotates. So we have to solve for the overall rigid body translation and rotation. Put all of this in a linear system. So I'll show you what happens. And so we set up this problem again to shed some light onto this dinoflagellate swimming, or the function of the transverse flagellum. But we also thought this was a very good, non-trivial numerical test problem, because we could solve, as I said, the kinematic problem using regularized Stokes-Slits. But we didn't do resistive force theory, but we could also use a more refined slender body theory. So that, if any of you know what that is, it's a little more refined than resistive force theory. So we could use this just to check our formulation.
I think that's the one with the interval cut off.
Yeah.
Yeah.
And then at the same time, what we can do is solve the full Stokes equations by building this thing out of points and springs and specifying changing rest length in such a way that we approximately achieve the specified kinematics. And we have reason to do that because ultimately, in all of these models, what we want to do is specify forces that come from internal force-generating mechanisms and then couple that to the fluid. So we thought that this was a nice, clean problem to work all of our magic on. Okay, so this appeared last year in JFM, but I'll show you. So here's the ring, and look at it carefully. So what's happening to it? Well, you could see it going up. It's in a loop. What you can't see is the rotation, because I have everything here colored white. So you can't see at the moment a material point rotating. So what's really happening here? So here are flow lines. So these are flow lines, and what's happening? What you're getting is like a rotating donut. So as the opposite neighbors, if you slice this ring, think of it as a donut. As these move, as the wave goes over them, they're doing something like this. It's not a rigid rotation, but as this wave moves, well, I'm turning it in the wrong way. You get an upflow like this, which should have been obvious. This is like a vortex ring. Okay? So you're getting, because of the action of its neighbors, you're getting this upwelling flow, which is pushing the whole structure up. So in fact, this longitudinal flagellum, what's most evident is the translation. If you cut out a piece, and I don't have a movie to show this, but if you put a mark on this periodic ring and you watch it go, here the wave is going in this direction, and you can see here's a time snapshot, here's another time snapshot. You do get translational motion. Yeah?
So here, well, at least as it seems to me, this flow upward is possible because there's a hole in the center of this structure. So if you would put or wherever you threw away from the start there, then probably this flow wouldn't be able to, well, to flow
Let's
the way it
see.
is.
Let's see. Okay, you set me up good there. Okay. So what happens? So I'll get to that momentarily. You understand what he's saying? It's not a free ring. There's a sphere in the center. Yeah.
So what decides if it's going up or down?
The handedness of the helix and the direction.
So and if you change the waveform, does it change?
We just looked at that simple sinusoidal waveform. So you mean so we looked at things like changing the pitch and changing that, and I'll show you momentarily. Did you have a question? Okay. So what happens if we change the actual radius of the helix? And this is the tangential velocity, and here, this is the slender body theory, and this is the Stokes slits. And we see that as we change this radius, the tangential velocity goes up like r squared. Okay, unfortunately, my longitudinal velocity is not showing up. I think that's the keynote problem. Okay, what happens now if we change the number of pitches on a ring? Okay, so similarly. Well, you know what happened before. You should get this optimal value. If you had no pitches, you won't get any translational velocity. And if you have too many, you won't get any either. So, Lord, I put this in Keynote, and my graphs aren't showing up. So suffice it to say, because I could show you afterwards, that the slender body theory does not pick up that optimal. Okay, but the regularized Stokes slit does. I should have tested this.
How many are optimal? How many are optimal?
Somewhere around 45 degrees, which you might expect. So here's the answer to your question, and I'm sorry, I think I uploaded that paper on the JFM paper on your documents, so you can look at the graphs there. But this is not in the paper, this is not published. What if there was a cell body? Okay, so let's see what happens. So now a few things have changed here. We are not using regularized Stokes slits any longer. This is an immersive 3D calculation. And what you see, in fact, this tube, this is not close to the sphere. We just put a sphere smack in the middle of there. And you see that the sphere itself is actually getting shot up faster. So,
Oh, so it's not mechanically coupled to the...
It's not mechanically
Then it's
coupled.
just a tracer particle, right? Then this acts as a tracer particle, which is just being convected by the fluid.
It's not a tracer particle, it's solid. It's
Changing the flow a lot.
It's changing the flow. It's not, so
It's a
this
big
here,
particle.
this here, it looks dark here, but it's discretized by a lot of points. Now, the deal with regularized Stokes slits, and I hope I've given you this impression, that you could solve you can write a code, and we have had many undergraduates work during summer projects doing very interesting simulations because they can write this code in a week. There are numerical issues that one has to deal with. What should the size of your cutoff functions be? What should epsilon be? Because you're looking at forces distributed on surfaces, like spheres, like rings, and there's an inherent discretization there. So how does that parameter epsilon relate, how should that be chosen with respect to the way you're discretizing the surface? So easily written, there are some subtle numerical issues. The answer is that epsilon should be chosen more or less equal to your discretization size. But but the regularized Stokes slits, when you write it in a quick and easy way, is an n squared problem, where n is the number of points. Because you're applying forces at these endpoints, and you're computing velocities at those endpoints, but the velocity at a point has to depends on each of the endpoints. So that's a double sum. Now, if you have more wherewithal, which we haven't done yet, other people have done, you could do a fast summation, you could do some fast multiple, or adaptive trees and so on. Somehow that work makes a lot of sense, but it loses the simplicity.
So you can take it to n log n.
Hmm?
Can you take it to n log n?
I think that you can. I think that Anna Karen Thornburg and Leslie Greengard have a fast Stokes slip summation that could be adapted to this. But I don't know what the constant is.
It's in log n.
It's in log n.
They're able to map it back onto solving, I think, 6 low-velocity problems. Using this Stokes.
But I don't know how many points you have to have in order for that to work.
That makes sense. Yeah.
So we did not, at the moment in our shop, have such a fast algorithm, and since we wanted to look at these interactions, we just put this into an immerse boundary solve, so that we can. So you see, actually, I think it's kind of interesting that sphere in the center gets shot out. This is not mechanically coupled yet. Another interesting simulation, which we haven't explored, is what if you put two rings aiming towards each other? Now, this is not the kinematic problem. This is done by springs, so there's fluid structure interaction. And I was hoping to see some beautiful dance that these rings would go around each other, but they just kind of smash here. More work needs to be done. So the conclusions here are that this undulating ring exhibits both rotational and translational velocities, and if you want to see more details, how it depends upon the parameters, please look at that JFM paper. And they also provide a very nice kinematic problem for numerical validation. So Hoa has built this nice structure where we have mechanical coupling, and the results are to be announced at a later date. Here's a pretty movie. There's actually a wall here, so we're using regularized Stokes slits with images, and I don't understand. So we put this as at an incline to the wall to see what would happen. I thought it might flatten out, but funny things are happening. Infinite number of simulations one could do to learn something. I don't know where to start, actually. Well, okay, so that's the Reynolds number, and in the okay. I want to move on from low to high Reynolds number now, to high-ish Reynolds number. But I do urge you, any of you who are doing some low Reynolds number calculations, that the regularized Stokes slit formulation is quick and easy. And you can get results that actually are good without too much investment in programming time. So I'd be happy to talk to anybody if they have a problem that they think could be formulated in that way. So did I answer everybody's questions about the rings? What do you think is going to happen when we mechanically couple the cell body to the waving flagella? I think it's going to show a faster longitudinal velocity. The other thing is, with these problems, if I showed you those flagella, they're more complicated, obviously more complicated. I think that some of them have little hairs on them, and as I was talking about yesterday, that could change directions of things. And on top of that, it's not clear whether they're free to move within that girdle of the dinoflagellate. It could be that they are somehow stitched to the cell body, and that could limit the
So
motion.
then the helical structure is just kind of coincidental in that?
You know, I've looked at different species. Some look very much like it's free, and other ones look like they're stitched to it. And this is not the kind of work that biologists have had much funding to do. So you would think that people have been looking at these organisms for a long time, but they're not. It's not characterized. So maybe it's up to the physicists to say, hey, let's look at the structure of dinoflagellates. They're everywhere. You can get. They're not hard to find. So let's just, in the time that I have left, show you Amazing Simulations 3. I don't know if these are amazing or not, but I'm just going with it. And I probably will I will have time to tell you about one particular type of undulatory swimmer. So, tale of two Reynolds numbers, I think I'll just tell you about one. And I will tell you about a collaboration with a group of biologists and neuroscientists and other mathematicians where we are trying to understand the neuromechanics of locomotion of lamprey. And so I'll show you some pictures of lamprey, and this is the cast of characters, and whoever is highlighted in green are postdocs who have done all the work. So one of the goals of neuroscience is to understand how does the nervous system control or create a complete behavior. And lamprey here are a favorite model organism because they are the most primitive vertebrate. Okay, they have their neural wiring has been studied in depth, and they're easy to deal with in a lab. They're kind of like eels. They're very, very ugly. Has anyone ever seen a real lamprey? So they're not free swimming beautifully in their tanks. They've got these big sucker mouths, and they're basically just when I visit Avis's lab, they're just like hanging out with their big sucker mouth on the side of the tank, and their bodies just flop down into the water. The way she gets them to swim is she has a yardstick with a little pin at the end of it and nudges them. That's not the nastiest thing that she does to these lamprey. So our goal here is to understand, and I talked some about sperm, but we want to do the same thing for lamprey, which is an actin-myosin-based muscle system. We want to understand how neural signals couple to muscle models couple to lamprey. And so this is philosophically very close to what Dan was talking about yesterday in his goal towards integrative models of the sandfish. So here is what a swimming lamprey actually looks like. You see the beautiful undulatory wave that's being passed from head to tail. And how is this happening? So the overall philosophy of this project is to look at the coupling of all of these systems. So we want to understand how the neural network feeds into the musculature with the surrounding fluid dynamics, and as the fluid flow changes, how is the animal sensing that, sensing its environment, and then altering its neuronal signals, and so forth. What I'll show you today is success that we've had where we left out that piece. So the next big thing, is to understand full coupling and look at sensory feedback. So Dan showed some of the EMG tracings from 3 stations on the sandfish. So let me tell you what I'm showing you here. Along the lamprey, imagine this is a schematic of the lamprey. And it has a center line like a spinal cord, a notochord, and then it has 2 families of muscles, left and right. left, right. And if you put electrodes at the different segments on the right and left side, here are the tracings that you get. So here's right 7. You see burst, 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 so on. Here's the 19th segment on the right side, and you see that you get that burst with a certain, you get that burst with a certain delay. So you get a wave of activation being passed along the right side. If you look at the segments on the left side here, left segment 719, you see that it's firing an antiphase from the right side. So what Dan showed yesterday, he had electrodes only on one side. It's a similar thing. There are opposing families of muscle segments, but here we have it mapped on both sides. So you have this structure, and you get electrical activity being passed along in a traveling wave on one side and an antiphase on the other side. So Avis Cohen, Phil Holmes, Kathleen Hoffman, and other biologists and applied mathematicians are trying to understand the electrical activity as systems of coupled oscillators and other such things, and trying to understand how each segment communicates with the other segment and so on. What we would like to do ultimately is to put in this understanding of the electrical activity as coming from coupled oscillators and put that into a mechanical model. One thing that I think is interesting is this. These are a set of new experiments coming out of University of Maryland. So what you see here is an excised spinal cord of a lamprey. Okay, you've got to do this very carefully, I suppose. You put it in a bath, and you put electrodes and measure the electrical activity. Even when this thing is at rest, it's obviously dead, you get firing, and you get a certain frequency of firing here. The experiments that they have recently worked on is this. Can you take this spinal cord and mechanically oscillate it at different regions at a certain frequency and alter the natural frequency of firing? And the answer is yes, it can be entrained, and it depends on where you wiggle this spinal cord. So there's some very interesting dynamical systems going on in this, in just the excised spinal cord. So just so you don't feel too badly about them killing these lamprey and taking out their spine, here's what they naturally look like. They are parasites. Lovely picture. Okay. So one other point, and this is what we were talking about at the end of Dan's talk, is that in lamprey and many other fish, the wave of activation, so if you measure this wave speed of activation, and you think that's talked about as fictive swimming, and you compare it to the mechanical wave speed that you observe, they're different. There's usually a phase lag. So one of the questions at the outset of this collaboration was the biologists asked, can we in models observe this phase lag without any sensory feedback? They thought sensory feedback was very important. And in fact, simple models, as Dan talked about yesterday, they do exhibit phase lags even without sensory feedback. So what I want to show you are just the basics of a full integrated model where we are coupling muscle mechanics, fluid mechanics, with electrical activity. So here's a bio lesson in my core understanding. Here's a muscle segment. We were talking about muscle segments yesterday, in Peter's talk. So motor, I guess. So here's a muscle segment like the sarcomere. There are these motor neurons that are attached to a particular muscle segment. And Imagine there's this burst of EMG activity and action potential comes in. When that action potential comes in, calcium is released from its internal store, the sarcomere. So calcium gets released, and then calcium causes myosin to bind to the actin filaments to contract. When that happens and it's activated after a while, then the calcium, the free calcium gets absorbed back into the sarcomere. So what we're thinking about is that there's a calcium-induced contraction of muscle. So here, what we do is, rather than going through the full voltage equation, any Hodgkin-Huxley type equations that couple voltage and calcium and so forth, we have a model that takes more of a phenomenological point of view. We look at mass action kinetics. So within a single sarcomere, we're trying to track the calcium dynamics. And so let's just look at one of these equations here, where let's say C is the amount of free calcium within a muscle segment. And what's happening? Like I said, there's calcium in the internal stores on the sarcomere, and so there's stuff attached here, and there's free calcium. When it gets released, it could bind to a muscle filament and cause contraction. So here's a simple system of ODEs with lots of rate parameters. But here, what does this say? It says that the rate of change of free calcium is this. It's coming off the sarcomere, so CS is the calcium bound to the sarcomere. It comes off at some rate. And this rate, this constant here, will be 0 if it's not feeling an electrical burst. And it would be 1 if it's feeling an electric burst. And then we're losing free calcium at some rate when it's binding to the sarcomeres, and we're losing free calcium when it's binding to the filaments. And F is the amount of free spaces along the filaments. Okay, so this I'm just appealing to your undergraduate differential equations modeling class, writing down a system of mass action equations. And we can write all of this down, and we have a nice ODE model, so that your question should be, how well do you know these constants? That's always the problem in math bio models. How do you know your rate constants? Well, some you make up, and some you get from experiments. So Thelma Williams is a muscle physiologist who's done experiments on single lamprey muscle segments. And so some of these we have a handle on. So I'm not going to go into this anymore, but you could reduce the system of differential equations to actually 2, calcium and bound calcium, and you have these kind of reactions. But what's important here is that what we're going to do to take an electrical signal and couple it with a fluid is by having just our electrical signal either on or off, which are changing parameters in this equation. Okay. Now we are going to track in each muscle segment the calcium, which will tell us, we'll relate that to how much force that muscle segment is creating. So here now, I'm about to show you some fluid models, but let's take each muscle segment and think about it in this type of Hills model. We're going to think of it as having passive elastic structures, an activation, which depends upon the calcium dynamics, and possibly a damper, or we're going to get damping from the surrounding viscous fluid. So here's the simplified lamprey model. Okay. It's got a center line, and it's got right and left muscle segments, and we're going to do something like this. We're going to send a wave of activation along each side. On, off, on, off, on, off. What does that do? When we have on, off, on, and so on at a particular muscle segment, we will be tracking the calcium. The amount of calcium that's bound to the filaments will tell us what the muscle force is there. We are also going to have passive elastic forces due to springs, stiff springs, and so on, and we're going to put that into a fluid. So let's see what happens. So here's the goal, here's the question. Can we build a computational lamprey with the following properties? It takes a wave of action potential as an input, generates realistic muscle forces. Okay, we don't want this thing exploding. We also want this structure to reflect elastic properties of real fish. Again, not lamprey made of steel or of foam. We want to have real bending rigidity properties. And can it swim? So this is it. So I'll answer this question in a moment, and of course it's going to swim because otherwise I would leave here. And this is number one, and number one. So this is complicated in this sense. This is an integrated model. The voltage pulse we're taking as an input. Okay, so that's simplified. But we're going to be looking at muscle models and elastic properties and the properties of a surrounding Navier-Stokes fluid. Trying to put all of this together. So here is our champion lamprey. There. Let me cut to the chase here. And I've told you at each segment we're going to solve a system of ODE. So let's look at this for a while, and I'll tell you what's lovely about these calculations. So this, he replays again and again. What's input into here and what's output? We are inputting the stiffnesses of all the passive springs. We are inputting the surrounding fluid viscosity. We are inputting the voltage square wave pulse. And on each segment, we are specifying rate constants that have something to do with calcium dynamics. We are starting this guy off flat, and then we turn the system on. He's starting up in a still fluid. We turn the system on by propagating this electrical wave. In the ODE system, that just tells you when K1 is 0, K1 is 1. You start that off, and he achieves a sinusoidal shape. What we are not specifying is the geometry that he achieves. It's a he, by the way. We are not specifying the speed of the mechanical wave. We are putting in an electrical impulse at 1 hertz. We're specifying the speed of the activation wave. Putting all this together in a Navier-Stokes fluid, we see him come alive. We see the beautiful vortex shedding. We get a standard Montana wake.
It's a reversed wave.
Reverse.
Compressed wave.
What comes out of these calculations, and we're specifying the viscosity. Well, what's the Reynolds number? Well, you can define Reynolds number in a number of ways. You could take your length scale to be the actual length of the creature, but he's about 12 centimeters. So this is, we have found, Mike, you won't like this, that we use dimensional units, because after a while, when you're talking to biologists,
You just get tired of it.
you get, it's such a headache. So we are actually programming, God help us, in dimensional units. I don't know how y'all feel about that. Because then, his length is 1. 1 what? 1. No, nothing. But anyway, dimensional units. So let's see what does come out. the Reynolds number based on the length and the wave speed is pretty big, 8,000. I prefer thinking about this Reynolds number as based on the diameter of the body and the speed of the tail going up and down, which is more manageable. Here, the wave speed over the activation speed is about 88%. And that changes depending upon certain parameters. I'll show you some interesting simulations very soon. Here's what Dan was calling efficiency, the swimming speed over the wave speed. And so this is a much more efficient swimmer, it's 0.65, right? Remember, Dan, what was he getting up? He was like getting 0.4. But, you know, that's...
0.35 or something, 0.35.
Yeah. So 0.65 is pretty good. And this is about what's observed. So I should show you comparisons with eels and so forth. The Struhal number is the swimming speed over the speed going up, down. So that's also in the ballpark. How are we doing these calculations? These are immersed boundary calculations, and I will tell you here, I owe all of the success of these calculations to Boyce Griffith and his adaptive mesh refined code, because we could not get this to work without refining our mesh near the structure and near the vortices. So this is these are higher Reynolds number calculations, and this isn't a very good, this is a little bit exuberant refining that I'm showing here, but we tag cells wherever there's an immersed boundary point or wherever there's vorticity exceeds a certain threshold and throw more accuracy at it.
So on the implicit solve, or on the projection, you use a multi-grid?
He's using PET-C solvers and with multi-grid preconditioning, but by CG stab. Yes. All right, quick eyeball convergence study. Certain number of level of refinement, twice level, third level of refinement, and same time step. Here's what we have. And I'll tell you why this is, why I think this is impressive. And of course we have the numbers to back this up, but this is a good eyeball convergence study. We started this creature out flat. We had no idea the geometry that it was going to achieve. And so here's different level of refinements, and you can see the shape is very much, is almost identical, and we got this nice vortex shedding pattern. Here's that. I don't want to talk about this. So now we can do experiments. We've got a working system. So now we're going to look at a swimmer that is twice as stiff, but at the same time we're going to scale the peak muscle force that it could exert. So this guy's twice as stiff and twice as strong, and he's smooth. But we'll compare in a minute. Now we're going to have a floppier guy, half as stiff and half as strong. First he doesn't look so good, right? But then he finds his groove. Let's compare. Here is a race. Stiffest, half as stiff, no, stiff, right. Stiffest. Okay.
Stiff, less stiff, stiffless.
Okay, let me just be clear. If you watch this movie again, you will see that the red guy, he's out of the gate fastest. Then after a while, they all start swimming around the same speed. So the red guy who popped away accelerates, and those guys end up.
So are they the same, doing the same parts or not?
No,
they're
that's
just,
a fun thing to do too.
no,
yeah.
but it was.
No, this is just for comparison. But of course, these are pictures, so we could actually look at numbers. And so let's just look over here for a minute. This is the swimming speed. So the green is the stiffest. This brownish color is the floppiest. You see the stiffest accelerates much faster. After a while, they pretty much end up swimming at the same speed. The other things that we calculate are also the work or the power that it took for them to swim like that. So in fact, if we look at the work here, the floppiest swimmer swimmer performs much less work. So, in fact, what happens here is the stiff body swimmer accelerates, but the floppy body swimmer uses less energy. So Eric Teitel, our biologist collaborator, claims that this is probably how barracudas were. Barracudas are predators, and they got to get out of the way fast. That's why they're stiffer. And you can have all these nice biological implications.
What's a barracuda?
Google it. It's a fish. It's a mean-looking fish. You don't know the song? Okay.
In
Now,
steady state, will they all drift about the same amount, or does that have something to do with the stiffness of the body?
I'm not sure. In that case where we changed this, we didn't just change the stiffness. We changed the amount. We also changed that along with the amount of power it could exert. So if we just took the maximal muscle force and just made it floppier and floppier, it would fall apart. So we changed two things together. So now let's look here for a second. This is, all I did here was change the activation wave rather than firing at 1 hertz, fire at 1.5. And changing that one parameter gives a very interesting change in the wake structure. So for those of you who look at high Reynolds number wakes, you'll know it. I can't even remember. This is a P2 wake. People characterize wakes based on how many secondary vortices shed at each stroke, primary vortices, and so on. And I think this is a, there's two, each time the tail flips, 2 vortices of different signs are shed. So if you look back at the previous wakes, this doesn't look like that. Michael, does this look like a von Karman, a reverse von Karman streak to you?
Nope.
Right. There you go. I woke you
So
up.
why does it go down? It doesn't go straight.
It doesn't go straight. That is correct, because there's acceleration, and it starts at when the wave that we send it is not symmetric, so it kicks off in a certain way. If we sent that wave flipped over, it would kick off in this direction. The other beauty of an adaptive mesh code is that you can make your tank very big. There's- Yeah.
That's what's usually, I think it's called an S2, where you have.
That's what I said.
Oh, I
Didn't
didn't hear it.
say
Sorry.
he wasn't paying any
I
attention.
jumped in.
We find this at S2 weight, and in fact, if you look at the PIV measurements that Eric did with George Lauder years ago, they show that they get this S2 weight behind heels. So just changing that one parameter changes the wake structure. And what the other thing that we're doing, I don't have time to talk about here, is that there's been a robotic lamprey built in Lex Smith's lab in Princeton as part of this project, and Megan Leftwich is the one who's in charge of this, and we are trying to compare the wake structure behind physical models of lamprey here, calculations, and PIV experiments of not real lamprey, but real eels. So we'll see how that goes. Here's a cool movie. So now we take our servo motors, our virtual servo motors, and try to turn them really fast. So rather than firing at 1 hertz, we fire at 2 hertz. And this guy can't keep up. So, and I think that, well, not I think, I know from Megan's robo lamprey, if she tries to make her servo motors work too fast, the thing just wiggles and okay. What else do I want to show you? We can put this in different viscosities. For the fun of it, we can look at the emergent geometry, and so here's much more viscous, and of course the vortex shedding is different. And here's a cool movie that I will end with. One thing that I find very interesting in sperm motility and in these, especially when we're looking at sensory feedback, is we talk about chemotaxis of organisms like spermatozoa. And we try to decide if they really are chemotactic or not. we understand how bacteria change direction by tumbling less, for instance. But larger organisms like sperm and so on, even in vertebrate sperm, they are chemotactic. How are they steering? I mean, he's swimming this way, he wants to go that way, and he goes that way. What are the mechanics? How are they changing their internal dynein microtubule action to steer? My question is the same for lamprey. How are they steering? So all we've done here, this was Chow Yu's fun movie, is that she just repeatedly made the muscles on one side be stronger than the other and flipped it around. So there's nothing steering this, it's just playing games. But I think this sort of idea about changing the activation strengths on either side might give us an indication of steering. And finally,
I have a question. Is
Yeah.
it now interacting with its own wake?
yeah, yeah. Right, because if you're going straight, the wake goes behind you, but if you go like this and then like this, and they do interact with them. So this is a very nice, even if I say so myself, computational experimental setup, and we could ask lots of questions even within this 2D simple framework. We want to look at different models of muscle activation. Lamprey don't usually swim side by side, but fluid dynamically it would be interesting to see how they interact with each other. But the reality is that this is still a 2D computation. So we are at the same time trying to look at 3D lamprey, but you know what? 3D is much, much harder than 2D. You haven't discovered that already. So we have a swimming lamprey-like structure that I've just shown you here. But here we don't have any of the bells and whistles. We are more or less specifying the kinematics. We don't have any of the muscle mechanics attached to it. And also, I mean, 3D is important, but you get so much data, and actually visualizing the vortex shedding and so on really needs a lot of time. When I will end here, and I will say that our group at Tulane is in the next year looking to hire at least 2 postdocs and 3 grad students to work in a new NSF-funded math and computational biofluids. So there's so many interesting problems to work on, and New Orleans, with all of its ghosts and music, is a very fun place. Thank you.
Questions, yes?
How important do you think the understanding the vortex shedding is if the weight is behind it?
Well, the vortex shedding is giving it its thrust to swim forward. So it's inherently coupled to all of the fluid dynamics. There are so it depends on what moves you, right? So there's a lot of people who care about that, but I think that's just part of the whole thing. There are models. I should have referenced it. So earlier on, before I joined this project, Phil Holmes and a group of others came up with a much more simplified model of this lamprey swimming, where he used something like a resistive force theory. And they got some very interesting results, but of course, with resistive or reactive force theory, you don't look at the fluid dynamics around you. So there, the wake structure was not even looked at. So you can learn things. It's just, how much more of the fluid dynamics and physics do you want to include?
In the real lamprey, the way, is it on a plane?
Yes.
So the 2D simulations that you do are
The 2D
good, right?
simulations for the body are good, but let's think about the fluid, that even if the motion is 2D, what that means is we're ignoring
There's
any
stuff.
Z dependence, right? So that's like a sheet, so you can't have fluid going around, right? You have just an infinite sheet. So I think you could learn a lot from 2D. but we always have to realize what we're leaving out.
Mm.
So just like with the sperm simulations, most sperm motility, most mammalian sperm show planar waves. Invertebrates show out of plane, but it's not enough to say that's 2D. Sure, that's 2D, but the fluid dynamics around it is.
Okay, let's thank Lisa. Before we go on,